Hello guys, so today I'll be solving this problem, which is four divisors. So the problem states that we have been given one integer array, and in that integer array we need to so it says that the number of divisors of the integers in that array that have exactly 4. Okay, so basically we have to take the summation of all the elements which have exactly 4 divisors. Okay, and we have to take the sum of the divisors. Okay, so if I look at this example, it's 21. Let's zoom down. Yeah, 21, 4 and 7. Okay, now in 21 I can see like it has divisor 1, 3, 7 and 21 itself. Okay, so there are 4 divisors. Okay, for 4 it's 1, 2 and 4. Okay, and for 7 it's 1 and 7 because 7 is a prime number. Okay, so here the count of divisors is 3, here the count of divisors is 2. Okay, so the only number which is satisfying the condition like exactly having 4 divisors, which is this 21. Okay, now here what I have to do is, so every number which is satisfying 4 divisors count. Okay, I have to take the sum of all the divisors. So here if I look, so this is like 1 plus 3 plus 7 plus 21. Okay, which is 4, 4 plus 7, 11, 11 plus 21, which is 32. Okay, so yeah, 32 is the answer here. Similarly for 21 and 21, so like we observed, so 21 itself is satisfying, so there are 2 21s, so 2 times 32, so that's 64. Here is the answer. So the concept that you need to know in order to solve this problem is prime factorization. Okay, so like this is a concept we have been taught in our schools, right? So what it says that if we have a number, okay, if so prime factorization basically tells that we have to express this number in terms of primes. That basically means it's a product of all the primes raised to the exponents in which they are expressing. So let's say there is a p1 prime number which is dividing n. Okay, so these so number of times this prime factor like this prime number will be dividing n, that will act as its exponent. Similarly for another prime number it can be e2, like that. For the kth prime number it will be raised to some kth power. Okay, so this is how we express prime factorization, right? So for example, if I have 24 as a number, okay, so I can express 24 as 2 to the power 3 times 3 to the power 1. Okay, so 2 is raised to 3 and 3 is raised to 1. Okay, so this is the prime factorization expression for 24. Okay, cool. So how to solve this problem? So one trivial approach is to iterate over all the numbers in nums. Okay, and basically like brute forcely check, okay, how many prime factors like how many divisors it have. Okay, so this is the concept one. So what we can do is, so for a brute force approach we can do something like this. Let's call it brute force. Okay, so I can iterate over all the numbers for LE in nums. Okay, now for every element what I can do is I can initialize a counter as well as a sum. Okay, now I can iterate over all the numbers which are less than equal to LE. So I equal to 1 to LE itself. Okay, then I can check if LE is divisible by this I. That means this element is a factor of or divisor of LE, so I can increase count as well as I can take the sum of, which is this I. Okay, and finally let's say this is my answer variable. What I will do is, if the number of divisors, okay, is equal to 4, then I can add up whatever sum I have gotten. Okay, and finally I can return, and yeah, finally I can return my answer. So this is an acceptable solution with respect to like without seeing the constraint. So this is an acceptable solution and it will work. So but if I write this code and if I hit a submit here, so it won't work, because if I look at the time constraint here, okay, so I have two for loops here, right? One is iterating over the number of elements we have been given, and then for each number I am iterating over 1 to that number itself. to check how many numbers are dividing that number, basically finding the divisors. Okay, so with that I will hit a time complexity of the number of elements I have been given times. So the maximum amount this can run is max of whatever number I have. So max of array. Okay, so this will give me a quadratic time complexity. Okay, so this will give me a happy TLE, because here the constraint as n can goes up to 10 to the power 4. Okay, and the maximum number can go to 10 to the power 5. Okay, so I'll be doing a billion number of operations. Okay, so it's a TLE. So we know like how to optimize this. Okay, so the basic idea is to not to iterate over 1 to that element itself. It's better to take the square root of that number. Why? Because so let's understand with an example. Let's say 24 it is. Okay, so I know 24. For 24, like 1 is a divisor, 2 is a divisor, 3 is a divisor, 4 is a divisor, 6 is a divisor, 8 is a divisor, 12 is a divisor, and 24 itself is a divisor. Okay, so if I look at the square root of that, okay, so square root of 24, this will lie in between square root of 16, okay, and square root of 25. Why I have taken these two numbers? Because these two numbers are perfect squares, right? So that's why. Okay, so square root of 16 is 4. Okay, so the square root of 24 will lie in between 4 and 5. Okay, if I take the seal of it, okay, so 5 will be here. Okay, if I cut this half, okay, now whatever numbers I have on the left half, okay, they have a partner on the right half. Okay, as I can see, for 1, 24 is a partner. Okay, for 2, 12 is a partner. Okay, and for 3, 8 is a partner, and similarly for 4, 6 is a partner, right? So I don't need to iterate over all the elements from 1 to LE itself. Okay, if I simply iterate over 1 to square root of LE, okay, so when I'm incrementing my count, I can do a +2. Okay, because I know for every number, okay, in the right half there is a partner, which means that right half element also dividing my element. Okay, so my inner for loop will reduce to for I 1 to square root of LE. Okay, what I will be doing is I'll find the, so my left half partner will be this. To find the right half partner, I'll be doing let's say partner, this will be LE times I. Okay, now I can check if I times partner, okay, is equal to LE. Okay, then I'll be updating my count with yeah, also there is a condition. It may happen the number itself is a perfect square. Okay, so with that I don't have a left partner and a right partner. Okay, the number itself will act as a square root of that. Okay, so what I will do is if I is equal to partner, okay, so I'll be incrementing my count by plus. Okay, and sum by I. Okay, otherwise if left half partner and right half partner are different, okay, then I'll be incrementing my count by plus equal to 2 and sum as I plus partner. Okay, now the time complexity of this is square root of max element we have in the array, right, which is better than this linear time complexity. Okay, so yeah, with that our optimized time complexity will be reduced to the number of elements we have, n, times square root of maximum element that I can encounter in the array, max LE I can say. Okay, a big O of that. Okay, now if I put down the constraints here, now n can go to 10 to the power 4. Okay, and the maximum element in the array can go to 10 to the power 5, and a square root of that will give me 10 to the power 2.5. Okay, with that I can express this as 10 to the power 6.5 operations I'll be doing, which is much better than a billion number of operation. Okay, and this will get accepted. Okay, because in any problem, okay, if you are hitting a time complexity less than equal to 10 to the power 7, it's acceptable. Okay, there are situations where 10 to the power 8 is acceptable, but most of the time it's not. And if you are hitting 10 to the power 9 kind of operations, then yeah, you will get a TLE. Okay, but yeah, this will not get a TLE. Okay, I think I have written TLE. Okay, this will get accepted. Okay, AC. Cool. So this exact solution, okay, I can show you here. Okay, in CPA algorithms, this guy has done the exact algorithm that I told you. So what this code is doing is, so it is taking a number and it is returning the summation of all the divisors of that number. Okay, so here the idea is it is iterating over all the numbers. Okay, like all the numbers which are less than the square root of that number. Okay, now it is basically checking the prime factorization of that. Okay, so this is a very cool algorithm. Okay, it's not the same as what I'm doing. Okay, it's a little bit optimized. So how it is doing is, so let's say for 24. Okay, so 24 I have 2 to the power 3 times 3 to the power 1. Okay, as a prime factor as a prime factorization. Okay, so here I can express 24 in multiple ways. Okay, so I have 2 to the power 3, so I have 3 different forms in which I can express 2. Okay, and for 3 itself I have one form. Okay, but to come to think of it, okay, this 2 to the power 3, okay, I can do something like this. I can take 2 to the power 0 also into the action. Okay, 2 to the power 1 as a exponent. Okay, 2 to the power 2 also, and 2 to the power 3 also. Okay, similarly what will happen is, so here 2 to the power 0, its partner will be 24 itself. Okay, here 2 to the power 2, its partner will be 12. Here 2 to the power 2 is 4, its partner will be 6. Okay, and here 2 to the power 3, its partner will be 3. Okay, so there are 4 different ways, okay, in which I can express 24. Okay, so it's basically 2 to the power 0 times 24. Okay, like that. Okay, so in each expression, okay, I'll get a different summation amount. For example, here 2 to the power 0 is 1, so this is 1 plus 24 is 25. Okay, so here 2 plus 12, I'll get 2 plus 12 14. Okay, and here 4 plus 6 10 I will get. Okay, and here 8 plus 3 11 I will get. So the summation of all that will give me the summation of divisors of 24. Now in each expression, since I'm getting a different sum value, what I can do is, so the number of ways I can express the prime factorization, okay, basically the factorization, not the prime. Okay, the factorization will give me the amount, the number of, or the distinct number of sums I can get. Okay, so here I can say the sum I can get is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 times with 3 to the power 0 plus 3 to the power 1. Okay, so if I take the summation of all this, so this is 25 plus 14 39, 39 plus 10 49, and 49 plus 11 60. Okay, so 60 should come as a answer. Okay, so if I look at here, okay, the summation of this, okay, this is so we can observe like this is a geometric series. Okay, I can say geometric series. Okay, and for geometric series we know how to find the sum. Okay, so this is the formula to calculate the sum of a geometric series. So here if I plug in the values, okay, the first element is 1 times 2. Now there are 4 numbers, 4 minus 1 times 2 1, okay. Now times for 3 also, so this is 1 times 3. Now there are only 2 numbers, so 2 minus 1 upon 3 minus 1, okay. So if I calculate this, so this is 16 minus 1 upon 1 times 3 to the power 2 minus 1, which is 9 minus 1 8 upon 2, okay. So this will come out to be 15 times 8 divided, this is 4, which is 60. So yeah, so this process is what has been implemented in this article, okay. So per number, it is basically finding the prime factorization, okay, and with that it is calculating the GP summation, and it is finally returning the total, okay. As you can see, so this is to find the exponent of a number, okay, or the divisor. Then for that exponent, it is calculating the GP sum of that, okay, and it is keep on multiplying total, okay. So yeah, so here in this approach, so the time complexity is square root of n, okay, which is same as which is implementation details that I told you here, the square root of max, okay. So yeah, you can follow this article, okay, and you can have this function where you can plug in all the numbers in the elements that you have been given, and with that this algorithm will give you the sum of divisors of that number, okay. And yeah, you can basically add up to your answer. So this is still good, okay, but if you are in an interview process and let's say the interview wants to pull your leg, okay, he will say, yeah, this is a good approach, but can you reduce the time complexity more, okay. So you can be in trouble, okay. But if you know, there's a very popular algorithm which we called Sieve of Eratosthenes, okay, let's call it Sieve only, okay. You can solve this problem in logarithmic time complexity, okay. So if you guys are not aware of Sieve, okay, I will say just go to any article. This is a very popular article, so whenever any prime number kind of a question comes into an interview, okay, just think like, okay, Sieve can be a concept that can help you to solve that problem, okay. Because the time complexity of Sieve is here somehow it's, yeah, it's n times log of log n, okay, which is much faster than the square root time complexity, okay. So I'll leave this article to you, okay, so you can go through it, okay. So yeah, so what Sieve does is it basically starts from a number, okay, and it proliferates to all its multiples, okay. So what I'm saying is maybe here only I think it should have a Sieve article, so let's call prime, let's open this. So yeah, so this is what Sieve does, okay. Let's say you have been given this expression, okay. Sieve is basically used to check whether like how many prime numbers you have in a range, okay. So what it does is it take all the numbers in that range, okay, then it starts from 2, okay. It claims that 2 is a prime, okay. Then whatever numbers are multiples of 2, okay, it basically rejects them from being a prime, okay. So from 2 we go to 4, 4 to 6, okay. All the multiples of 2 which are in that range, okay, it basically rejects them, okay, but it keeps 2 alive, okay. Then in the next iteration, okay, we have 3 here, okay. Now 3 is a prime. Now whatever multiples of 3 are there, they are not prime, right. So it rejects all the multiples of 3, okay. And when it reaches 4, okay, it already knows 4 is not a prime because it was rejected in 2, okay. It skips that, then it comes to 5, then from 5 it again proliferates to all 5 multiples in that range, okay. and like that whatever final expression you have, okay, it will contain the list of prime numbers. Okay, so this is the implementation details. Okay, it's a very short implementation, and you should like learn about Sieve, okay, because in interviews it can happen. You may be asked question related to primes, and Sieve will be your helping concept. So yeah, so we can easily apply Sieve here, okay, because as we saw, okay, so from a prime number, okay, it reaches to all of its multiple, okay, and it rejects them, right? So what we can do is, instead of rejecting them, we can have another array sum, okay, that will uh, add up all the uh, divisors, okay, for a number. Okay, so what I'm saying is, I think it's basically it will be easier if I can show you in the code. Okay, so basically I'll be applying sieve. Okay, so what I will do is, I will first find the maximum element that have been present. Okay, so I'll say max that equal to so I'll be coding in Rust, okay, but the concept is same. You can apply in C++ or any other language, okay, that you prefer. Okay, so first, in order to express the range of numbers that I have, I will first know like what is the maximum number I have. Okay, so I'll say nums iter max, then I'll say unwrap because it returns a option. Okay, then as usize. Okay, I'll be using this as an index, so that's why usize. Okay, then I will have two arrays. Okay, I'll say let mut count. Okay, so this array will help me to store the number of divisors of a number. Okay, so I'll initialize to 1. Okay, why 1 I will let you know, but yeah, and another I will store the sum, which will store the sum of all the divisors. I will also initialize to 1. Okay, so why I am initializing to 1? Because in Sieve our loop starts from 2. Okay, now we know that 1 is already a divisor of all numbers. Okay, that means if I'm starting from 2, I already have a divisor, okay, which is 1. Okay, that's why, since I'm not considering 1 in my loop iteration, okay, I'll keep 1 initialized to all the numbers, okay, and also sum. Okay, then I will write sieve here for I in range 2 to max. Okay, then I will say let mut j. Okay, then I will start proliferating to all of the multiples of I. Okay, I'll say j. Okay, this is the starting multiple of I, the number itself. Then while j is less than equal to max. Okay, I'll say for j, I is a divisor, right? Okay, because j is a multiple of I, that means I itself is a divisor, like I is a divisor of j. Okay, so since I got a divisor here, I will update j is like the number of divisors of j by +1, plus equal to 1, and the sum of divisor of j with I. Okay, cool. Then I will increase j to plus equal to I. Okay, basically the next multiple of I will be what? So if I have I as a number, okay, the next multiple of I is 2 times I. Okay, similarly the next multiple after 2 times I is 3 times I. Okay, which is basically I plus I, then I plus I plus I. This is what we are doing. Okay, so yeah, with that I'll be populating the divisors count as well as the sum of divisors. Okay, then it's pretty simple. Now since I have this pre-processing done here, I will iterate over all the numbers. Okay, and before that I will create an answer variable, let mut ans equal to 0. Then I can iterate over all the elements for nums. Okay, now I will say if count of this is yeah, le as usize, if count of the number of divisors of le is 4, okay, then I will add up the sum of all the divisors to my answer. So sum of le as usize. Okay, then I will return ans. Now if I run it for all test cases, it throws me error because I got excited and I wrote a another x, like extra x. Cool, so let's run it for test cases. Yeah, to, yeah, this becomes use size, so yeah, this needs to be of either do, so either do. Cool. So initial test case pass. Now if I submit, and voila, it got accepted. So here, so this is the sieve logic, okay, which means the maximum element that I have, okay, I'll be running it max times log of max, okay. Then I'm simply doing the number of elements iteration, which is basically the big O of n, okay. So my square root time complexity reduced to this expression, okay, which is much faster than my number of times of element. Like this is lesser than, I cannot claim it is lesser because there are test cases where this time complexity can become faster, okay, if the number of elements are pretty low and the maximum element is also very less, okay, then this might be little slower. But if you think about asymptotic time, where I have large number of elements and also big elements, okay, then this will always be faster, okay, this one, okay. So I can say this is much lesser than, okay, or this has a lesser time complexity than this square root approach, okay, only for asymptotic constraint, okay. Cool. But in this approach, if I look at the space complexity, okay, so here I was not using any space, okay, it basically the number itself, there are only variables, okay, so it was using 0 space, okay. But here I need an extra space of I'll just erase this, of the maximum element I have, okay, and that is of twice, for storing the count of divisors, and other for storing the sum of divisors. So space complexity wise, this is little hefty, but yeah, we go off max. But time complexity wise, okay, this is much faster than this, okay, considering asymptotic constraints, okay. Cool. Now if you guys have doubt like how this loop is a logarithmic time complexity, okay, so I will suggest you to uh, learn about sieve, okay, and try to take a pen and paper and try to see how many numbers you are actually touching here, okay. uh, you will be surprised that you are basically doing a harmonic series here, okay. Okay, and the summation of harmonic series is a logarithmic expression, okay. So I'll paste the article, I'll paste this article, okay, and it basically shows like how the time complexity of sieve is calculated, and like with the help of harmonic series, okay. So yeah, I think I just saw this article which was giving this time complexity analysis. So yeah, so this is the way how time complexity of sieve is calculated, and the reason why sieve is n times log of n, okay. Cool. But yeah, the idea being is, if you know sieve's algorithm, your code will be pretty less, okay, and it will be much faster than all this square root time complexity. Cool. So this was the Rust implementation. Now a similar implementation I have done for Go, okay. So in here also the same thing. First I am calculating the maximum element in the array, then I am updating my count of divisor as well as the summation of divisors, okay. So here the changes. So here I was initializing all of them with 1, but in Go you cannot initialize the array, okay, or everyone will be initialized to 0, okay. So I'm manually initializing them here, okay. Then I'm keep on updating the count of divisors and the summation of divisors, okay. And this is pretty identical to the Rust implementation. Basically iterate over all the elements. Now check the count of divisors. If that is 4, then whatever sum of divisors you have gotten for that number, add it to your global answer variable. So yeah, if I submit this, voila, it also got accepted. This for Go. Now if I show you the C++ code, I think it's much lesser. Only 17 lines of code. Okay, maybe that's less because there is classes and public involved. I guess some 15 lines of codes here. Cool. So here also I'm first finding the maximum element, then I have this sum and count. Okay, then I'm using sieve algorithm to update the count of divisors and the summation of divisors. Okay, and yeah, finally I'm just checking over elements, whichever one has a count of 4. Okay, number of divisors as 4. I'm basically updating that with my answer, like updating my answer with the sum of all the divisors. Cool. And finally I'm returning answer. So this is the C++ code. Now if I submit, it got accepted. Cool. So that was the solution. Okay, so we went through the brute force approach, then we went to one optimization approach, which is the square root approach. Okay, then I also told you, like, let's say this is not the problem. Okay, let's say you have been given some number and you have to quickly find the summation of this. Okay, you can apply this geometric series shortcut to find the number of divisors you can have, and also the number of ways you can express the number. Okay, so this is a trick that you can use. Okay, then finally we went through sieve approach, which was much faster than the square root approach, and it's always faster than the brute force approach. So yeah, that's the logic. So if you like the solution, please do subscribe to the subscribe to the channel, and you can add any comment if you think I missed something, or you are finding difficult at some part to understand. So just comment it, because I will read that comment, then it will act as a feedback for me, because in the subsequent follow-up videos, whatever I will be developing, your feedbacks will help me to build more clarity content, right? So yeah, that was it for this video. And yeah, also happy new year to you guys. So we are 4th of this January, so it's a new year. Just build some goals, try to achieve this in this year, and yeah, just keep on lead coding. It will help in interview as well as debugging skills. Cool. So stay tuned to watch more videos. Bye bye.